Chem. Your Unit 3 test is coming up, so as always, another review. Hello. So first off, we're going to be talking about IMFs, or intermolecular forces. So intermolecular forces are basically just a Coulombic attraction between two dipoles. Dipoles literally just means two poles, hence the name di, which means two, and pole, which means just charge, so two charges. So what this can literally mean is you can have a positive charge here and a negative charge here, and they will attract each other. I don't know why I did that. And they will attract each other, like so. Uh, Another consequence is that you can also have, like, say, a positive charge here and a whole bunch of molecules that have negative, 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 and like all around it, right? And so that's a and so that's a thing you can do with that's a an example of IMFs, or intermolecular forces. The two that I just showed you were the strongest ones, ion and ion dipole. Right now, and the third strongest, it's actually a special case of the fourth strongest, is hydrogen bonds. So what hydrogen bonds are, um, they are among the they can only happen among very large electronegativity differences. So what happens is if you have an NH, an OH, or an FH, these can form hydrogen bonds with not like that, like with N, with O, with F, and other atoms of the type. Just control Zing my way there. And College Board doesn't care if you spell out the word hydrogen or H. They don't care. What College Board really is looking for is, okay, they understand what it is, right? The next one. So if this is 1, 2, 3, the next one, 4, is going to be dipole dipole. And what this is really just talking about is literally, let's say we have a molecule here and it's polarized, right? It has a permanent dipole moment, aka it's polar. So if we have a positive here and a negative here, another molecule will have a negative here and positive here because it's attracted. And opposites attract, basically. It's Coulomb's law. And number 5, these are very weak forces. However, without them, many liquids and many solids would not exist. Think about butter, think about oils. They're held together by this force, which is called van der Waals, or London dispersion forces, LDFs. What this means is that at any point in an atom, the electrons might not be totally evenly distributed, right? It might form a temporary dipole with a partial negative on this side and a partial positive on this side. And so what this can do is, in another atom, another neutral atom, right? It can shift the electron density over here, right? It can shift the electron density sort of like over here, such that these then become uh, attracted to each other. And this is instantaneous, right? This is going to be very, very quickly. However, it is very important because many nonpolar solids, right? Nonpolar, if you remember not having a charge, many nonpolar solids rely on this in order to stay, well, solid. Without this, many nonpolar solids would not actually exist. Think of your butter, your oil, your waxes. Anything that doesn't have like a permanent dipole moment could not exist in a solid or liquid state. Sorry. And so this is actually a very special case of IMF, and it's because it's actually very dependent on surface area. So you can imagine, like, if I if I do something like this, right, where each joint represents like a carbon atom, this is going to have a lot more London dispersion forces uh, than this, right? Because this is more clumped up, it's more spherical, whereas this is more of a line, and so it has more surface area. And this is why sometimes you'll see London dispersion forces as depicted as dependent on molar mass. And so the molar mass will actually increase the amount of London dispersion forces that you experience. And London dispersion forces, they are everywhere. As let's see here, they not only apply to nonpolar molecules, they can also apply to polar molecules and even ions. Because again, it's all about that all about that uneven distribution of electrons that happens at any given moment. So an atom could quite literally go from uncharged to charged based on electronic vibrations. Okay? So that's definitely going to be on your test. Next over here, I have solids, liquids, and gases. So what I'm assuming here is that what they mean is like the differences between those. So solids, liquids, and gases are actually very different. You might have seen this in your fifth grade, your sixth grade science class. Uh, if you remember, solids are very tightly packed. Liquids are kind of like less tightly packed, maybe like one down here, and then gases are just fully random, right? But what happens actually with solids is you have a lot of nice like little neat charges, right? So if we go like plus, not plus, 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 minus, you'll have minus plus, plus minus, and this continues going down, minus plus, uh, that will repel, plus minus, minus plus, and so on, right? And so this would be what a solid is like, very organized and very compact in its charge distribution. Let's just go one more, just for the heck of it. And so this is going to be what a solid is like. It's maximizing its attraction between its atomic neighbors, such that it can actually stay solid, stay very compact. Now, what a liquid is it's basically like if you have it's basically like a solid, but if you introduce like a little bit more vibration, right? So you still have your base plus minus, right? My uh, plus minus minus uh, minus plus, but over here, if you noticed, I this will actually be more indicative of a minus plus over here. And so this actually repels, and you can actually get a little bit more vibration out of a liquid. Right? And gases, they are fully like out, right? They are fully random. What gases can be, I'm gonna use spheres, right? These do not have any attraction between them, well, technically they do, but like at this scale, it's very negligible, right? And so you have solid, very compact, and it also maximizes the attraction. I spelled it wrong. Whereas a liquid, it's less compact and doesn't actually maximize attraction as much. It's more of like a min max, you know? It's going to be more of like an attraction here or repulsion here. However, they're still very attracted to each other. And gases, they are fully like they are as not compact as you can be, right? Uh, not compact at all, basically. And these basically have little to no attraction at all. And so these are the three states of matter that you'll probably have learned in your 5th, 6th grade science class. There's one more, that's plasma. It's basically ionized electrons. Very, very like rare cases where you actually see chemistry operating with plasma. If you get into nuclear chemistry, that's an option. But for the most part, within the bounds of AP Chem, you won't need to know about plasma as much. So the next thing I have here is KMT, or kinetic molecular theory. Now KMT, right? It's basically just describing gases. So gases under KMT have no size, or size is negligible. Uh, no attraction, or no stickiness, as I was taught. Uh, Basically no IMF. And these are like the very core of KMT, right? No, very negligible size and very negligible IMF, right? So what this can be, this operates under very high temperatures and very low pressures, and so this gives rise to the laws of very famous scientists like Boyle or Charles or Avogadro. Now, what Boyle's law basically says is that pressure is inversely proportional to volume, right? Its PV is equal to a constant C so long as T and N remain constant, that is temperature and moles, respectively. Okay? Now, what Charles said was that the volume was proportional to temperature, V equals BT, so long as pressure and moles remain constant, right? And what Avogadro said was uh, that volume, or pressure rather, I guess, is proportional to moles, because if you remember Avogadro's number, he was all about the moles. So basically, P equals Cn, right? Rather AN, I should say, because we've already used C. And so this operates under that temperature and volume were constant. Okay? And so if you combine all of these together, you get PV equals NT. However, this doesn't actually work out in real life, and that's because we need another constant called the ideal gas constant, R. And now R is in units of liter, whatever your pressure is. I'm going to use bar. You can use atmosphere. You can use kilopascals, pascals. liter bar per Kelvin mole. Now, the reason why we use Kelvin instead of Celsius in this case is because it doesn't really make sense to have negative pressure times volume, right? Because if you think about it, negative PV can either mean negative P times V, which doesn't make sense. How can you have negative pressure, or P times negative V, which also doesn't make sense because how can you have negative volume? And so that's why we use the Kelvin scale, which is an absolute scale of temperature, right? And so you have pressure times volume is equal to moles times Kelvin times your R, right? So this is given in your AP equation sheet. You're actually given the value for R that they're going to use most often, which is actually R in units of liter atmosphere per Kelvin mole. At least I'm pretty sure. I'm pretty sure that you're given. They wouldn't exactly expect you to memorize it. But for your overachievers, that is 0.0821 liter atmosphere per Kelvin mole. And this is basically what KMT is. It boils down to no size and no IMF, right? And so what you can actually do is a lot of times you can boil gas questions down to what does this say under the ideal gas law, right? You're given temperature, volume, pressure, and you're asked to find moles. You can rearrange the ideal gas law such that it gives you moles. You're given pressure, volume, and moles, but you're asked to find the temperature. You can rearrange the ideal gas law to give you temperature, and so on and so forth. Basically, every single variable here can be solved given the other three. Okay? And so, now, moving on. Solutions and mixtures. Now, I was told by Mr. Ruby to give, or by your teacher, Jinx specific, obviously, you can skip ahead of this video if your teacher already covered this. I was told to give special attention to this part because this part he hasn't taught yet. So now, what solutions are, and I'm going to give you a formal definition here and basically an informal definition, and here's the formal definition, and I'm going to type this out: a homogeneous mixture of two substances. Sorry, I was blanking. Which behaves different, which behaves very different, which behaves like the solvent phase, sort of thing, right? It basically boils down to a homogeneous mixture of two substances. Now, if you're confused about what that means, don't worry. Basically, what a solution is you have a solvent, usually it's water. It's literally just whichever substance is greater. There's more of. And the solute is whichever one there's less of. Whichever one is less of. And so these make up a solution. Now, for examples of solutions are going to be like sodium chloride and water. Hexane in CCl4, carbon tetrachloride. We don't use this solvent anymore because it's basically cancer juice. And these are all solutions. Now, mixtures, on the other hand, is a more general term, right? A mixture, not mixed year, is basically uh, two substance, two substances uh, to get like in the same container, basically. And these actually have two types, right? You can have a homogeneous mixture. It This is your solution, right? And you can have a hetero. And this is are your suspensions. Spell it right. And your colloids. And basically everything else but a solution. Uh, you can think of it like homo means the same, right? And hetero means different. And I'm sorry, like homo, like homosexual, gay, basically. Heterosexual means straight. You're attracted to the same gender. You're attracted to the different gender. I'm sorry if I offended anyone. That's basically how it goes. So all you have to know is homo means same, hetero means different. Genius literally just means phase. So if you're a homogeneous mixture, you are in the same phase, and so everything is mixed evenly, and you have a solution. If you have a heterogeneous mixture, you are in different phases. So think of a solid and a liquid, or a solid and a gas, or a liquid and a gas, anything like that. Homogeneous mixtures are basically just like solids and solids, liquids and liquids, gases and gases, right? Air is a homogeneous mixture. Um, your average your average salt water is a homogeneous solution mixture. Heterogeneous mixtures are literally everything else. Uh, you made a you made a pasta and your sauce, and you're asking about your sauce. That's a heterogeneous mixture. Usually, that's going to be an emulsion. You're asking about your ferrofluid. That's going to be a heterogeneous mixture. That's iron filings suspended in a oil in usually an oil-based uh, solvent. Uh, Basically, these two make up everything else that isn't a solution. Now, there are some interesting properties that come up with solutions. I'm gonna erase everything here. So, solutions, they have some very interesting properties. For one, they can conduct electricity usually, though not always, because, well, that requires ions. And if you notice, sugar water doesn't exactly conduct very well. And that's because it doesn't break down into ions. Sugar water is literally just sugar in water. I mean, it is a solution, it just doesn't conduct very well. So, this is going to be a solution of an ionic compound, usually. Uh, what can they can conduct electricity. Uh, usual, usually conduct electricity. Uh, I'm blanking here, of course. They can like have different volumes. What I'm talking about here is miscibility, and I say it like that because Because if you watch Crash Course Chemistry, uh, another series, a series on chemistry, highly recommend, right? Um, if you have water and you pour in methanol, CH3OH, and say you have 50 mils of both, you'll notice that it doesn't actually go to the 100 mil mark. It actually goes up to like the 97 mil mark. And this is what is called miscibility. Basically, any two liquids that are alike in properties, like they're polar, they can hydrogen bond, basically anything like that is miscible. Uh, there's they're gonna have like interactions with each other, and so that's where the missing 3 mils are coming from. Up next is properties of photons. Now, photons, if you know, are particles of light. And they exhibit very, very interesting properties, right? For example, light can behave as a particle. Uh, what it can do is like it can carries a distinct amount of energy, usually abbreviated H nu. This is nu. Everyone meet him. Nu say hi. They can't. It's a Greek letter. Nu basically means frequency. Why don't we use F? I don't know. It's confusing. Uh, this is the amount of energy stored in a photon, and it is a distinct packet of energy. Otherwise, light behaves like a wave. And yes, this is very confusing. However, it does you very much good to understand the properties of waves, such as diffraction, refraction, basically anything with waves. So, light can diffract, right? If you know about the double slit experiment, right? And I'm gonna draw the thing up here because I'm lazy. What you actually get when you shoot photons through here is it's not like two bands, right? It's actually more of an interference pattern with like bands here, 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 and so on, right? You actually get more of an interference pattern rather than just two slits of light. And this is very interesting because it means that there is some sort of wave-like property instead of just particles. And so, what this can actually mean is that light can diffract, it can refract, and every single property about light, it usually comes from waves. It usually comes from light behaving as a wave. Now, what'll happen, and this is actually what AP Chem really wants you to do, wants you to understand, is called the photoelectric effect. And this is where we're introduced to our good old pal, Einstein. Now, Einstein, he recognized that electrons can rip light can rip electrons off metal. Sorry. Uh, if you have a metal, you bombard it with light, electrons leave the surface. Bada bing, bada boom, that's the photoelectric effect. However, he noticed something very interesting. Using the classical definition of light, you have waves like this, right? And like using the classical definition, a greater amplitude would mean a greater energy. However, no matter how much in amplitude you have, if it's not like the correct color or above energy, then the electrons stay put, right? If it is the right frequency or above, then the electrons will be ripped off the metal. Now what's happening here is light as photons bouncing off the metal and ripping the electrons along with it. And this is what's called the photoelectric effect. Basically, E, not E equals mc squared, as you've told, E equals h nu. This is Planck's constant. It is equivalent to, get this, 6.626 times 10 to the negative 34th joule seconds. Now this is important because energy is measured in joules. Frequency is measured in 1/seconds. And so what you have is you multiply these two together and you get energy. Now, I'm going to shift gears here a bit. We're going to come back to this. And I'm going to talk about wavelength, lambda. Lambda is inversely proportional to frequency. A greater wavelength, and you have less frequent, and you have peaks and troughs coming less frequently. That's basically what wavelength is. However, if you know the speed of a wave, it's usually calculated in terms of lambda nu. In other words, wavelength times frequency. And if you have a light wave, that speed is equal to the speed of light, c. And so what you can get is c is equal to lambda nu. You can have nu is equal to c over lambda. Lambda equals c over nu. And this is what we're really interested in here. Nu is equal to c over lambda. If you remember, E equals h nu is is our energy equation. And so we can plug this in and get E equals hc over lambda. This is what is usually given to you on the AP test and on many standardized tests, actually, dealing with chemistry, is you're given a frequent wavelength value, usually as a color, as something else, as like nanometer values. You're gonna have to convert those into meters. It's really confusing. Nano, in case you don't know, is 10 to the negative ninth. Okay? And so what this is the energy equation given a wavelength, right? Because these two are constants. And so we can do a little bit something called spectroscopy. And now this is totally unrelated to the photoelectric effect, but I do wish that you still remember that. Okay? Now what spectroscopy is basically measuring light. Now, if you remember, right, from your 8th grade class this time, that if I have blue here, that means that it is reflecting blue light, not absorbing blue light. It is reflecting blue light off the object and into your eye. And so what spectroscopy is it basically measures what color it is. However, it doesn't measure it exactly in what you would expect. Instead of actually having like a visual sensor right next to the light emitter, it has a visual sensor on the opposite side, right? So if this is a light emitter, right? It has a visual sensor here, which we'll mark in red. So it comes through. Everything but blue is passed through, and blue light is reflected. And this reads, no blue light was passed, right? And so this is what we call absorbance, A. Now, if you have absorbance v wavelength here, right? A v lambda, and this is going to be all across the visual spectrum, right? From R to V, Roy G. Biv, literally. And sorry if it's a little bit disproportionate. it's like I can't draw. Can't draw. Basically, what'll happen is like you have a massive peak at blue, and it like kind of tapers off, but not really. And so this is what absorbance is all about, right? You can, if you set this to emit a certain color that is particularly absorbent in this solution, then this will read, oh, a lot of light was absorbed because I can't see anything. Uh, and so what will happen is that the absorbance, and it's actually related to a couple of different things. Usually you'll see this as A, B, C, literally. This is the molar absorptivity constant. Uh, sometimes you'll see this as like a backwards 3. This is epsilon. This is molar absorptivity. This is unique to every solution, and it basically just tells you per mole what is going to be absorbed. Uh, B is usually path length, and C is concentration in moles per liter, because concentration is literally just how much stuff is there per unit volume. Okay? And so what this is, molar absorptivity, it is in units of uh, molar, uh, molar, inverse molar, inverse centimeters, because path length is usually in centimeters. And there's a unit for absorption, but I forgot because I'm human. So this is what's known as the Beer-Lambert law, or Beer's law, if you're trying to shorten it. And given molar absorptivity, path length, and concentration, you can figure out the absorbance, basically. And now this all depends on your chosen wavelength, because usually what you'll do is you'll put it into this sort of machine that has this setup, right? You'll put a cuvette in, it reads, and you're given an absorbance value, like let's just say question mark here. And this machine really operates best under conditions where the A max is equal to 1, because of course it does. And so if we're going back here, right? Usually these will be the best values for your experiment. And now I hope that my explanation has been particularly satisfactory. If you have any questions, you can call me, or Google exists. And as always, pass your test, ace your exam.